thank the organizers sincerely, because I really appreciate being here. Great that you put this together. I had a great time up to now. I had a very good time last night. So I may talk nonsense once in a while, but okay, you might not know this. Probably you won't. So this talk is about well, it says stability estimates for the localizer index, and the whole thing started last year when I went to Sint, and more or less on the first or second day, Alex asked a few questions, and one of the questions was, we now use this localizer quite a lot in many situations, and successfully in many situations where we don't have a proof that it's supposed to work. Notably, usually what we did with Terry was to prove that the localizer has an open gap so that you can use its signature safely in situations where the Hamiltonian had a gap. But you could also have systems like heterostructures which have no gaps, extra surface loads, and so on, and nevertheless use the localizer locally. And you can look at spectral flows a little bit. I mean, like in Alex talk. So he would like to know why the localizer why the localizer works so well also in these type of situations, and also why it's so stable when you perturb the Hamiltonians somewhat far away from the tip of the localizer. So how to prove stability estimates with respect. So that was the first question, and I'm going to tell you how to go about that. And that's a joint paper with Alex, which is out there. And the second question that he asked, okay, I use the localizer, and he said, I want to use localizer also for quantum Hall systems, Maxwell equations, and things like this, which are unbounded operators. And well, it has been puzzling me for quite some time to understand how to deal with unbounded operators with localizer. And I think I can report some progress on that. It's not yet finished completely, but I feel safe enough to talk about it today. So, and the other guys that I lived well, I mean, Terry is not here now. He knows the talk probably. Tom is here. The others, they are students of mine, which are all people that I collaborated with on the topic of the law. So, I do know we had quite a few talks already on this, but let me nevertheless, start from zero so that the few people which are not doing it regularly here. I mean, there are a few which do it, and many which haven't used it that much, also have a chance to understand it. And to make things simple, let me talk about a two-dimensional system, and let me first talk about tight binding models to be on the safe side. So the Hamiltonian is going to be in 2 dimensions on a lattice with some finite dimensional fibers. And here's the spectral localizer that you build from it. In dimension 2, you have 2 position operators, first and second component. They commute, as Terry pointed out. I can shift them by adding a little x, which sort of centers the positions at some point x in physical space, little x in physical space. And then, well, these are 2 off-diagonal entries, which are scaled with the parameter kappa, which play an important role in the following. And on the diagonals, the Hamiltonian, but well, you see with 2 different signs. The Hamiltonian actually centered around some energy, which you can think of as being lying in a gap, but you can also think of situations, different situations. Right? By construction, this thing, if you just look at it, well, it's first on infinite volume here, on the full Hilbert space. It's a self-adjoint operator. It's not a difficult thing in this situation. It is going to be a difficult thing for unbounded operators, but here, the position operators are self-adjoint, unbounded operators, and the Hamiltonian is just a bounded perturbation, so immediately you know that this is self-adjoint. And well, the situations where we're interested in is that we have a gap. I'll talk about this gap. This gap is, so to say, the thing which makes the signature index of the localizer topological quantity, which requires some stability due to the presence of this gap. Okay, so we want to understand why there is. And then you look, okay, so this is the infinite volume thing, and then you want to put it on the computer, and for that we want a finite dimensional matrix out of this. So we just basically take a finite volume, which is here just a finite box of the finite number of sites in this box on the lattice, yeah, and you project by basically just taking theoretically boundary conditions there, and this gives you a finite dimensional matrix, and the spectral localizer index is that you just look at the signature of this divided by 2, so the number of positive minus the number of negative eigenvalues, and divided by 2. Well, this is this spectral localizer index, what we want to talk. And as pointed out by Alex, this is easy to compute because you don't need to do spectral calculus of this thing. You just need LDL decomposition to compute the signature, and it was very easy and fast to compute that on a computer. And the stability, I already said that, of the localizer index is measured by the size of this spectral gap. Okay. Now, this was something that Terry worked with, but when I came into the game, the question was how is it connected with the more conventional index theoretic objects that people have used. So either Chern numbers, which come from differential topology. Here is Chern number that is computed in K-space for a periodic model. Well, we know that these Chern numbers here, they can be connected by an index theorem to a Breton index. And this goes back to Kohn and Belisar very long time ago already. And okay, so the main theorem or the main question that we had in those days was to understand the connection between these two objects and the spectral localizer, what Terry was already computing. Okay. So this index theorem, just to point out, also it works not only for periodic models, but you can write these also in a non-commutative framework by, well, actually here I did rather. If you do that, you compute the matrix elements of this operator here, where P is the projection onto the Fermi level, and take its trace and take its expectation value, and then this thing makes perfect sense. And it is actually also by ergodicity the same thing as the average of this quantity here. It's basically just a rewriting, a little bit of algebra behind. And this is what people also call the Janko-Ressa local marker, which is basically the same thing which appeared in the index 20 years before. It's just the disordered average of the local marker, Janko-Ressa. Anyway, in this very general framework,
but the Ressa doesn't take the average.
He doesn't take the average.
So
that's why I said
so
it's the average local marker.
Index fluctuates. So
that's right. That's right. But if you take sufficiently, it does fluctuate, but it takes sufficiently large volumes, you can make some sense of it. I know you wrote a book about this.
yeah, because the thesis is like this index, but they should be aware that it's not. So it fluctuates.
Yeah. Okay. So we have this index theorem, and the theorem with Terry was a criterion to show that this spectral localizer index is equal to the Chern number and the Breton index. And there are some criteria. Okay, so the first criterion that we put in is that the Hamiltonian at that energy E has a gap of size little g. Okay, so we ask the system to be an insulator. We ask the Hamiltonian to be homogeneous, so that the Chern number and this index make sense. We can get away a little bit from that, but let's suppose that for now, it's not the main point. And then there's a condition on this parameter kappa and on the parameter rho. And before going on, let's not take too close of a look. I will discuss this in just a second, but whenever this kappa is sufficiently small compared to the gap and to the non-commutative derivative of the Hamiltonian, then we do have precisely the theorem that the localizer index is equal to this Chern number, and therefore okay. Now, and we can even prove a quantitative estimate on the size of the gap of the localizer, which is all blue. Okay. Now, as I said, you need H differentiable. This just means that the commutator of the Hamiltonian with positions is a bounded operator, which just means that it's a sufficient slow decay. I mean, can be very slow actually. So then this is just a finite number, and well, the gap is whatever it is. And then I just need to make the kappa in the spectral localizer sufficiently small so that the right-hand side of the bound is satisfied. And the left bound here is satisfied at just rho is sufficiently large. I just make sufficiently large mode. I'm on safe grounds. And practical situations, these kappa doesn't need to be very small, like 0.1, or it is sufficient. You have to play with it a little bit. The estimates that we get here, they were not really optimal. So the openness of the gap is valid also for more parameters than the one that are provided by this estimate here. But practical purposes, as I said, I mean, kappa 0.1 or sometimes 0.01 is okay, and sizes of size 20 is also typically sufficient to get topology out. So the way that we prove the theorem involves two steps. There's an analytical step, which uses tapering estimates, and I'm not going to talk a lot about that, but there's an analytical, something analytical to work, and then there's more like a topological argument, which has the flavor of an index argument, or you can say also it's a K-theoretic argument. So the first proof that we had was with the K-theory of fuzzy spheres and index theorems connected to that. And then afterwards, we came up with a proof by spectral flow, which is much more simple and elementary, I think. And now, more recently, there's a bunch of proofs. I'll tell you who that is, who also understood that basically the spectral localizer is just a Kasparov product. So you can, if you know Kasparov product and its properties, you can also derive the same theorem. I mean, the topological part, not the analytical. Analytical is something. I'm not going to talk about a lot about variations of this. I mean, first of all, I will say how you do it in other even dimensions, but you can do the same thing also in odd dimensions. You can compute also weak invariants. You can compute Z2 invariants. Terry told us how to compute Pfaffians, invariants which are connected to these systems with invariance properties. Con and I wrote a paper about semi-finite pairings. So there's very many variations, and these are not all of them. I mean, Alex had a bunch of others already on his slides. Yeah, question. Yeah.
So how about looking at this thing as a pairing of K-theory?
I will talk about that.
So once you show it's a pairing, it has to be.
That's right. That's right.
So you don't need a gap. Any estimate of the gap.
No. Okay, let me comment about that a bit later.
Okay.
I think the gap is very important. I mean, you already understand that if I want to compute a signature and to have something stable out of that, I better have a gap. I need a projection on the positive, on the negative side, and the difference between these classes is the outcome. What the localizer does, it tells you that I can compute it in finite volume, which is not obvious because you have an infinite number of eigenvalues to the left and to the right. So you can compute like in differential geometry, they call this, things like this in regularized situation, an eta invariant. And basically what we tell you is that this eta invariant is computable in finite volume. Okay, and it works very, very general. So you can do this for any integer valued index here. Good. So this is the story. And here's the equation for those. I mean, many have seen this slide of mine, of course, but some might not. To give some intuition, what happens is it's good to take the localizer and look at the Hamiltonian as a mass term. Okay, so I can turn this mass term on by adding a coupling constant lambda, at lambda 0. I get an operator which is basically just a dual Dirac operator. It's Dirac operator in Fourier space on the Brillouin torus after Fourier transform. And this operator has completely symmetric spectrum, and it has eigenvalues, well, which the spacing of which is roughly given by the parameter kappa, which was in there. And it's perfectly symmetric. It doesn't have a gap, so there might be 0 in the middle. But when you add a mass term to it, you're familiar with what happens. The mass term opens the gap. This is exactly what happens here as well. So you add the mass term on the diagonal here, it'll open again. The point is that this mass term is not just a constant mass, but it is a topological mass term, it's called like that, which opens the gap in an asymmetric way. So meaning that from the low-lying spectrum here, if you turn the lambda on, there's a spectral flow going on. There might be more eigenvalues moving to the left than there are to the right, inversely. And this spectral asymmetry, okay, determines this basically what happens with the lower eigenvalues there is precisely what we're measuring with the signature. Okay. So this is the picture, and you can actually also make a rigorous argument out of this. Okay, working with beta. Good. Now, I already said it, my first sentence was that, okay, how about heterostructures? Okay, where Alex has used this index successfully, and it worked. And the question is, why doesn't the theorem guarantee me, or his question was, why doesn't the theorem guarantee me that it actually works? Okay. So here's the criterion. I mean, this is the localizer written out once again here. And here's the criterion that I had. So if I have an interface, the heterostructure, the gap is 0. So already the right-hand side here is closed. So I'm stuck. I can't do it. I can't. The theory doesn't apply. And even if the position is very far from the interface, the gap is always closed. Okay? So there are just but nevertheless, it works. And the other thing is, for example, the other question, so to say, is if I make a perturbation W to my Hamiltonian, which can be very large, but is far away from my center X, the little x here, one would expect that the local index is strictly local, so it doesn't depend too much on what is far away. This is actually something that was observed, of course, also numerically. But again, this is not in the it's not attainable by the theorem, because this means that if I make it larger and larger, well, the Hamiltonian, the norm of the Hamiltonian will grow, and then this thing here will be larger and larger, and I just don't get any stability in that regime. Okay, so I want to answer these two questions. There are two improvements necessary for that. The first one is I should be measuring a spectral gap somewhat locally for the Hamiltonian, so that I can say that my Hamiltonian has a local spectral gap. And the second thing that we will do is we will see that actually it's sufficient not to have bounds on the Hamiltonian here, but relative bounds with respect to the position operator, or the Dirac operator, which is basically the position. And if you have that, once you get far away, I mean, it's clear that perturbation which is far away is going to be damped by this relative bound here. Okay, so these are the two improvements. So let me first explain you what the local gap actually is. And before doing that, here's just a very brief slide how you go in general about the construction of the localizer. Structurally, again, I mean, we have these position the position operators. We built this Dirac operators with liquid algebras. Has in even dimension has the symmetry property here with gamma d plus 1, and then using this gamma d plus 1 with the localizer, and then you get the finite volume restrictions, as I said, by going in a general situation again to the using spectral, partial isometries on the range of the spectrum of the low-lying spectrum of the debug operator. Okay. Good. So here's how we define a local gap, and it's a very easy thing, naive, but it works. If you take the Hamiltonian and you restrict it on a finite volume, you will have, of course, surface modes around. Okay, obviously, and these modes, they will destroy the gap. Okay, but if you take one way out is to say I take periodic boundary conditions. I can do that. It's a bit more complicated. What is even better, and I think, and easy to check also, is that you go to this finite volume and you take the square on the finite volume box here, centered at x. You square it, and once you square it, the modes, the boundary modes are frozen out. Okay, they're not there. Sorry, not frozen out. I mean, there's simply no surface modes. And you square first. You first square. That's right. So there's a difference. Here, I first restrict to finite volume, and then I square. But here I say, well, let's first square, but a small matrix, not a big one. I just want to do it locally for, say, volume 20 or 30 or whatever. And then I can have a positive gap here, which is strictly local. Okay, so this G, best bound, lower bound that you have here, is what we call the local gap at point X, because the ball is centered at X, of size rho. And well, this was stressing what Terry was saying here about these two things. They're not the same. So the square does not have the ground set, and I'll show you that it works, the whole thing. I mean, of course, this G only depends on the Hamiltonian in this ball, maybe a little bit outside, but not far. Okay. So it's really a local quantity. The second thing is, as you increase rho and you keep the Hamiltonian fixed, you can check that this thing decreases. I'll show you a numerical plot in a second. And another nice thing is that if you know that all these local gaps, they are uniformly bounded below by some constant G for all X, you do get back the global gap. Okay, it's a little argument using tapering functions here. But here's a numerical illustration. See what it does. So you take Haldane, I mean Alex took a Haldane model, 80 by 80 sites, and here's the density of states. Not so interesting, but here you put your thing in the center, and here's the local gap as a function of the radius. As I told you, it goes down, and it's stabilized, not zero. This is one. Okay, that's the way that the gap is normalized here. Okay, so of course, asymptotically, as rho goes to infinity, I'll go to the bulk gap if I had a material which is very and if you take a heterostructure like this one, so you have here trivial, and here trivial massive graphene, and here you have a Haldane structure. You can go through. You take a window which is small, so 12, maybe this size here, and then you move the center through, and you see the gap will do the following. I mean, you come from the outside, and then you have some gap here, which is basically the gap of this material. And then you get closer to the interface, the gap goes down, and this here is approximately zero. And then it goes back up to, well, the bulk gap of the material on the right-hand side. Okay? And this is, I mean, very simple illustration. Simple. It turns out that this thing, this local gap, can be put into the estimate of the localizer. In some sense, this solves the first problem. And yeah, so I don't want to talk too much about this, but I mean, the second improvement which we do is that this is a slide just for the experts like Terry. We always work with these tapering functions. And why that? What is a tapering function? A tapering function is a function which has this property that it's looks like this. I think we have it here. Here's -1, and here's 1, and then here's 1/2, -1/2, 1/2. And you need a function which sort of is 1 here, and then it goes down smoothly. And if you take such a function, tapering function, you can localize the Hamiltonian by pulling it down smoothly, yeah, to the outside. And you then scale it. by this parameter rho. And the crucial estimate that you get when you take the commutator of the position operator with the Hamiltonian, you can look in Fratelli-Robinson, you can bound this thing here by the commutator of the Hamiltonian with position. The 1 over rho just comes from the scaling, but then there's a constant up front, and this constant, well, depends on which function you choose here. And the function that we always chose before gave us well, something like 8. But you can do better. You can get actually to 2 by doing the following simple thing. You take a function phi, which goes from 0 to 1. No, sorry, what was this? No, it's a function between, just take a support between 0 and 1, particular form with the parameter k, which you can optimize over. You integrate it, normalize it, you get a function phi, which is just half of this, and then you subtract the other half. And in this way, you get optimizing over the parameter k here, which there's you get down to 2. Okay, so it's a factor 2, factor 4 that we improved the estimate, and actually Alex verified this is almost as good as you can get. Can't get much better than that.
Sorry, Herman, I don't understand. What is the meaning of a small x?
The small x down here is like just a real variable.
Okay, real variable.
It's just
Like
one parameter. Indeed, before this is one-dimensional analysis. And the way that you do this here is just by Fourier. You go in Fourier space, and the general estimate is okay. You take the function f that you have here, its derivative, and then you Fourier transform. Okay. And it's L1 normal that is the quantity controls in there.
Yeah, I have a question.
Yeah.
Did you come up with this reduced field from somewhere?
No, this we tried. I mean,
I'm just curious.
I mean, this is a very natural, no? I don't know. I'm sure this is written somewhere. Come on, yeah.
Not that natural.
You'll ask ChatGPT.
No, I did not ask ChatGPT. Maybe ChatGPT will give me 1.999, but I would be actually surprised. I think Alex said 2 is close to often.
I just tested a bunch of these, yeah. I think
Anyway.
if I were to do it tomorrow, I would use a polynomial, not an exponential too. So.
No, I think it's important that this thing here is important because it is. Yeah, I did have some experience with Jeffrey function a long time ago, and this is as good as you can get in some sense. You could say, okay, I put some other powers here, but you'll find out this will not. I mean, like this one here with x square, and there also a square or even higher powers. But if you do that, you will realize the estimate will not improve. Okay. Okay, so, well, this is, as I said, technical. So here's now our here, and it looks more complicated, even though similar. And I have to walk you through a little bit what the improvements actually are. So the first thing is that we work with the resolvents. Now you see the resolvents of the Dirac operator here. There's a true imaginary part here and a constant up front, which depends on certain things. And we have the Hamiltonian with respect to this resolvent. Okay, so this will damp the perturbations which are far away. Also, the other part here, so the derivative, will also be damped by the resolvent. It's very natural from also many other perspectives. The second thing is that we get bounds, lower bounds on the localizer gap, which are given by the gap of the Hamiltonian, the local gap of the Hamiltonian. Okay, so here there's the local gap now. You can do that at any volume, local gap. And the d here is just some number which is smaller than 1. And then there's another parameter a, which, okay, enters here in a complicated manner, and the constant c, which you compute on it. But believe me, this is a general form in which there are many, many limiting cases which are of interest and which are helpful. So this is the best estimate that we could get. So in particular, coming back to this CF, which is here, to get back to the situation that we had before, we had a global gap. A was 0, B was 1/2. That's the way that Terry and I did it. And then the constant that we got was 12, and now we get down to 8/3. Okay. in the infinite volume. But as I said, I mean, the main point is that this can be done now in finite volume, and it controls also something in distance. I mean, perturbations which are far away are controlled in a nice way. Okay. And we did also some numerical tries. This is quite good, actually. So I can't do the whole proof, but I want to rather go to a point which I addressed already, and also is connected to what Emil said. There are two bounds here, and in some sense, the bound on the right-hand side here assures you that the infinite volume localizer has a gap. So this is of K-theoretic importance, where the bound on the left-hand side is something which tells you how you work with these tapering functions. It tells you something about the locality of the localizer. And I want to explain you how we get these relative bounds, because having these relative bounds is, I think, of great interest also for what follows afterwards. And also because it's nice. Okay. So for the relative bounds, we get the following theorem. So this is at infinite volume, and let's set also position and energy equal to 0. So things a bit more easy notation-wise. So the bound is just this thing. The kappa should be smaller than this, which is a limiting case of the general thing that upper bound that we had. And what we get out is that the infinite volume localizer is bounded by the Hamiltonian gap times this p squared, which is summed up as 1. Okay. And well, this is, of course, looks much simpler, this bound, and you'll see in a short while why you can cut it such a simple bound. It actually can be recovered from this general thing. If you set A equal to 0, CF equal to 0, because you don't need to interpolate to localize. And then the G cubed here cancels with this G, gives you a G square, and then only remains this thing, and that's the constant which you get out there. This is simply what you get. Good. So one way to understand this also is, as I said, it's important that you get a bound on the gap of the L, because this is important that you get out of the product, in this case, of two even KK classes, again, an even KK class, which is the difference between the projections. And this was actually, understood recently by Jens Kart. Ram and his student Lee did the odd case. And there's a recent paper by Kuhn von Dungen, which does both, and which is in some sense much nicer. It really explains very well, I think, why the spectral localizer is starting with the crossword product. So the main point is I want to show you how to get this gap. Okay, and this is one slide with some sort of an argument, a proof, and it's very simple. That's why I can show you. So here's the localizer, and we want a gap, so we just compute it squared. That's what we want found for below. So I just wrote out, and then you multiply out. You get the Dirac times the Dirac. This gives you a Dirac squared times kappa squared. And then there's h times h. Gamma squared is 1. And h commutes with gamma, so this disappears. So you have the h squared. This one here is positive, no? And then you have the commutator. The commutator comes from the fact that the Dirac operator anti-commutes with gamma. Okay. So let me call this thing here B. And now use the fact that the Hamiltonian is get from below. So h squared is positive. So all that you have to do is to assure that this positivity term here is not destroyed by this commutator. Of course, this guy here is positive. I can't just drop it. But what I want to do is I want to control this, and I would just bound this here by a norm. I would not get the relative bound. It would be the bound on the commutator of p with h, which is not good if h becomes large. No. Okay. So how can you get the relative thing here? Well, you split this little bit of positive thing here into one piece which you want to get out. So this is the b squared g squared that I want, plus a rest, 1 minus b squared. Okay. And then, okay, you combine it with this thing here, the kappa d squared, which I'm not going to throw away. I combine it in such a way that the sun, I mean, this term here can be written as we have the resolvents of the Dirac. I take the inverse of the resolvents and square it. Okay, this is precisely this term here. Okay, 1 minus b squared g. I mean, it's just that if you compute, you have something like g squared plus h squared plus b squared. I just write it as I guess ig plus d times ig minus ig plus d, something like this. Okay, that's trivial as that. You have to pay attention. But why is this good? Because then you take these things out and you put the resolvents onto the b, which is this term, and then you do have the relative bounds with the b's. Okay. So there's the commutator of the position with the Hamiltonian, and I do have the resolvents of the Dirac operator on it, and it damps this down. Okay, so I control the error much better. So all I need is that once I wrote it in this way, is that what is below in this bracket here is positive, and for this I need this thing back here to be less norm than 1, which means that this operator RBR, so the resolvent on the left and on the right on this commutator in norm is bounded by, well, the inverse of this coefficient here, and that's basically this condition here rewritten is what I had as the simple condition in the slide before. It's basically just this. Okay, so it's extremely simple. Okay, good. Now, here's something nice of this simple argument. If you now think of the Hamiltonian as an unbounded operator, this argument sort of works exactly in the same way. Why? Well, I mean, I'm going to not take my relative bounds with respect to just the Dirac operator, but I'm going to take my relative bounds with respect to the localizer itself. Okay? And then I do the same trick. The algebra looks a little bit more complicated, but what I will get is that here I have resolvents of the localizer. Why is that good? Because the resolvent of the localizer decays in space and in energy. Okay? So it's like an X, I mean, you have the Hamiltonian and the positions. They think of them as X and P, and you want an operator which has a compact resolvent. So X squared plus P squared is 1, is the harmonic oscillator, and it decays. And here we have the same kind of situation. Okay? So you can take in infinite volume, again, the spectral localizer, but there's a supplementary difficulty. The supplementary difficulty is that before even starting using the spectral localizer, you better assure that it's a self-adjoint operator, and that's not quite so obvious because I take the sum of 2 unbounded operators here. Okay. However, now we're in the world of differential operators. So Dirac operator, I can do a magnetic Schrödinger operator, I can do a Maxwell operator. Then this spectral localizer, given by the same formula, is a self-adjoint operator, and it has compact resolvent. So to prove something like this, there's a paper by Maslin that we talked about. I didn't like the paper that much, and not because of the thing that you complained about, but it is a very complicated criterion that they had. And I actually found quite an elementary proof that this operator is self-adjoint by using this KLMN theorem, which is quadratic form argument, which is Greek-sided. You have to do some, you have to work a little bit with pseudo-differential operators in order to use the elasticity estimates to do it, but I would say it's a standard argument to do that.
But the Maxwell operators are not in it.
That's right. There you have to do something extra. Okay,
Yes.
There's something extra, but it works.
Okay.
I checked. Okay, you have to deal with the. Okay,
Okay.
You're perfectly right. I'm aware of that.
Yeah, no.
Okay.
Talked about.
So also the maxwell operator, okay, the localizer will not have compact resolvent because it has this huge kernel, but you can't squeeze the kernel out. If you do it right, and there are wrong ways to do it, then you will also get a compact resolvent. So compact resolvent is important. Why? Well, also again in the realm of KK theory, you want to fall in the ideal, so you want to get something compact out. So I better verify that the thing has compact resolvent, and this again is this coercive exit estimates. You know, you have in this case I have a pseudo differential operator which has decay in phase space. The symbol has decay in phase space, so it's like the harmonic oscillator. And then you open books like Hermann or Schulz-Baldes' book, and it says, okay, when you have an operator which has a coercive symbol, then the operator has compact resolvent. Okay, so we're set. So we can do the computation that I did before, and then you get, by roughly the same argument, modified a little bit, criterion that if kappa is small, I can work now with the resolvent of the localizer itself. If this thing here is satisfied, this boundary is satisfied, I get an open gap. Okay? So again, the K-theory classes. So this is an infinite volume, and now we have to connect the thing to something that you do on the computer. Now, Alex tells me, okay, I do that all the time. I know. I just use discretization methods. There is a Maxwell equation. There's this Yi lattice that they use. What was it called? Yi, no?
Yeah.
And he said, look, it works. It's okay. For me, this was not sufficient. So I have to say I spent a very long time, disproportionate amount of time to understand the next slide.
Before we go, so here.
Yeah.
So you pick up the top K-theory class. How about the lower?
I didn't think about those yet.
Do you think you can get wiki variants?
Yeah, to be honest, I hadn't thought about it, but I would be surprised if not. I just haven't thought about it. Okay. I thought about the point which comes next, namely discretization procedure. Okay, but for the strong invariants for a moment. I'm absolutely sure that I can also do Z2. I mean, all the other strong invariants, like Z2 invariants, will go same recipe. It's just implementing the symmetries.
Because here, for example, if you put up periodicity, then you get the whole, which is torus, then you get higher topological invariants, but they live on this mixed space. One is in the continuum.
Yeah.
On the torus. The other one is
I understand. Yeah.
And you'd like to fish out all of them because they are all interesting.
Okay. Yeah. So I have not thought about that yet, but I'm sort of. I mean, the whole thing is so natural that I would think that you can do it. I'm not sure whether I'm going to do it, but so now, okay, I already told you. You need localization in phase space. So what did we do before? We took our localizer and we cut it in space only because the energy was bounded anyway. And we just took all energy states and, we just had the finite volume restriction. Finite volume was really the volume in physical space, okay? Because we just used the Dirac operator, which is just basically the positions. Here, I do need to cut off an energy, which they do anyway. I mean, they don't compute all states. And how do you cut off an energy? Well, I mean, you do just type binding approximation. Yeah. So basically, you do the grid approximation. You discretize your operators, and that automatically also cuts off in energy. Okay. So you can do this, and you can look in you can look in numerical analysis books. So in particular, there's a book which is called, it's by Brenner and Scott, which I like very much, and which I studied in detail. And I was, there you will see a lot of things about frame conditions, strength X conditions, and so on, which tell you, and interpolation polynomials of different type, and Bramble-Hilbert lemmas. It's a complicated story, but I believe that this whole story will allow you to complete the results that I tell you now. also in a more complicated and also more general way. But the very easy way to go about it is to work with these wavelets. So there are wavelets. I mean, there are many wavelets, and Ingrid Luboschi's is always known for this because okay, she got more famous. But I think okay, Yves Meyer is a very good harmonic analyst who's still active. But Alex Grossman is, I know, he was Marseille. He's sort of the grandfather of the whole thing. He had the main idea how to do this. And it works just like this. And you'll see, I mean, estimates are very easy to get straight. You take a function, phi, which we call the mother wavelet, which is such that in Fourier space, its Fourier transform has compact support in an interval minus 2 pi pi. Okay, so it's I would choose something like this. Okay, and then all you do is you shift it n times h. H is the scale at which you want to resolve. So this is the grid that you work with, and this is just the normalization factor. If you do this, you get an orthonormal basis because automatically by this construction, you get what people call the frame condition. And moreover, automatically with this choice, the strain fixed conditions are satisfied, which are something which is more complicated, which people used when they did these interpolation polynomials, which asked the Fourier transform to have zeros, not only at the, I mean, outside of the interval, but at an integer number of points. And okay, people just didn't know that. I had the feeling that they should use this wavelets as an easy tool to do that. So then you go like you would do. You could either just open the books, yeah, but I did it by hand here. You take the Hamiltonian from the, let's look at the, first look at the Laplacian. You discrete, I mean, you take the standard discrete Laplacian and you scale it by 1 over h squared. You take the potential, you just discretize it. For this to make sense, the potential here should be at least Felder. So this alpha will play a role in the second in the estimate. If you go to Dirac operators, I mean, first of all, magnetic operators, okay, there's a way also to do this. I don't perfectly understand yet. So I should say magnetic operators, I don't control yet. But for Dirac operators, which are chiral operators, it's important for the discretization procedure to work to add a Wilson term. So the Wilson term is well known because it, first of all, it assures that the topology is the right thing. That okay, you get the right binding numbers in one dimension, and in higher dimension you get the right topological invariance, whatever it is, yeah. But also, it's extremely important that this Wilson term, which is just a little Laplacian times gamma, so it does break the chiral symmetry. It's important for the estimates of the discretization procedure. Okay, so here's the estimate that you get out by using really these operators. You take the partial isometry from the wavelet states onto the lattice. Okay, tensorized with the matrix degrees of freedom, which there might be. And well, you want to control the resolvent of the PDE operator. And we compare it by embedding the resolvent of the discrete operator, so just discrete Laplacian plus discretization of the potential, plus eventually possibly the Wilson term, which you embed using this partial isometry in the larger Hilbert space. And the nice thing is you have norm-resolvent conversion. This thing here is bounded by a constant, which may depend on z, times h to the power alpha. The alpha just comes from the alpha of the potential, times the counter term estimate here. So this flows up as h goes to 0. If I make the t sufficiently small, it's controlled. Okay? And you do have norm-resolvent conversions as h goes to 0. What does that mean? Well, I mean, if I want to compute Chern numbers in particular, I can use the tight binding approximation because the Chern number, I need the projection. I take the compact loop around the band that I'm interested in. Because I have norm-resolvent convergence, I know that the projection from my PDE operator compared to the projection of the tight binding operator are close. Okay, so this is just uniformly bounded then after doing the contour integral. And
I think Ori has a few papers about the convergence.
he does, but not on the churn numbers, I think.
Ah, okay, okay.
Okay, and moreover, they work.
Oria.
Oria has, but I think so. I looked at this paper. I think Shu Nakamura was the one who's. I mean, I think Oria just made things more complicated. Okay? And this paper by Shu is very nice. It sort of lines out the things that I also did. Okay, and but what is also very nice is that you can. I mean, you can do this for the Hamiltonian, but you can do the same thing for the localizer as well. It's basically just the same argument. Even though there's the unbounded position operator, it doesn't change anything. I mean, it's an alpha continuous potential. You just compare locally into itself, so it's not a problem. So again, I can use the thing that I think Alex used it. Well, he didn't use wavelets. He discretized in a different way, but I know it works. You know, you were computing these things down here, and these things do give you the right topology. So this is still on infinite dimensional space, but now I can use the arguments from before to compute it. Okay, it's on the lattice. So now I'm getting to the end. Here's my resume. I wanted to tell you that we have new estimates on the stability of the localizer index. Well, really stressing the locality of the animal. And I showed you how to get, how one can get tight binding approximations for linear elliptic pseudo-differential operators and their localizers via weights. This is a bit what I believe, and it's like Inuit's question. Okay, I do believe that this immediate, I wrote out things up to now for the even case. I'm sure that it also works in the odd case. I'm sure it works with Z2 invariants. I think we could do spin churn numbers and the like, non-Hermitian situations. Okay, not sure whether these other things are so, whether you have models in continuous space where you want to do that.
Both of them.
Yeah, both of them are okay. So then maybe I should write the further proofs. But
We did it. You're an author on one of those.
That's yeah. But this was a lattice model, huh?
Photonic crystal.
Well, yeah, okay. Yeah. You see how much I understood of the paper. No, yeah. Anyway, I think for me this was worth going through the pain of this discretization procedures once. Now I know.
Yeah,
On his own state grounds, it works. He does compute quite. Thanks for the attention.
Questions or comments?
I have a question. So first of all, just not a question, but more like a comment. If you ever talk about this in the presence of like actual analysts, people from semi-classical analysis, you probably should call this the tight binding approximation, because the tight binding approximation is kind of different.
Is what?
It's a discretization. It's not a tight binding approximation.
Well,
I think I agree.
so what would you call it, rather? Discretization?
Yeah, tight binding. Not that every physicists get this. Let's just say they're vague sometimes. Okay, sometimes when they say they're doing a tight binding, they're just finding a discrete model that sort of matches some other thing. But properly done, you're actually trying to approximate eigenstates of the crystal as a linear combination of eigenstates of the atomic eigenstates
Yes.
together. And if you go through that procedure, that then is the tight binding approximation. And that's one way to get to discretize it. And it's not always available, especially in like in photonics where there's no orbitals to be binding. Yeah. And so I think discretization is
Discretization would be better. I mean, it's basically, this is the numerical analysis procedure that I went through. Okay, so, and you get it in the strongest. sense that you can wish for. It's important to get normal resulting conversions. Otherwise, I can't get the topology out. Okay.
Okay, so that was just remarks. And my actual question is, do you have any examples of Hamiltonians which have non-trivial numbers?
Yes. There's this.
Photonic systems.
I mean, photonic system, but I mean, a Schrödinger operator, say, for periodic potential.
Sure.
I mean, that
I showed you.
it doesn't break time.
I showed you.
No, if it's matrix valued and the matrix valued potential is has complex entries.
Okay, maybe. I mean, okay, maybe it's not easy to find an computable example.
No. Like the whole reason anyone studies any of this is because of Hall conductivity, the quantum Hall effect. So it's a 2D electron gas, a totally unpatterned background potential in a finite magnetic field.
Yeah, but I have to say so.
Magnetic field is actually.
Yeah, so I have to say the magnetic field is the only thing which I didn't go through yet because the approximation schemes I have to redo them. They might be more complicated. So I do know this theorem here. Okay, also for magnetic operators. Here I can really write it, but this procedures at this theorem here of the normal reserve convergence for magnetic Schrödinger operator, there's a question mark. I don't really know yet in detail. Okay. For Maxwell, I'm fairly sure I can do it, but there's also it's not worked out. Okay.
Yeah, Maxwell also has some other problems as far as I can understand.
But can you go the other way around from discrete back to continuum? So can you take a non-trivial model in the discrete case? Haldane model or something?
Yeah. At some point, I tried to look up. Alex, you know a model which has discrete approximation, the Haldane model? It shouldn't be too complicated to do that, actually, with some spin-orbit coupling.
I don't. I mean, I think that going back from the Haldane model to a real material, you have to like undo the DFT that you need to get there. So I think there are materials that look like, what are they? The anomalous quantum Hall insulators. I think is like the modern language for them in the 2D material community. I don't know why we were keeping.
Anomalous, yeah, when you don't have the external method.
Yeah, and so I think these materials have been found, but I don't think it's simple to undo like the DFT discretization.
Yeah. If you want materials, or you're happy with old chemistry, you can put together systems that. This has always blown my mind. You have this simple type binding approximation of something, and then you say, let's simulate the type binding approximation with cold atoms. So it's done there, but whether you want to call that a material or not.
Any other question for him? Not. Thank you.